everyone. So welcome to this week's ECE Colloquium. And today we are very honored to have the Professor Vijay Krishna Narayanan to give us the talk. And Professor Narayanan is the Robot Node Chair of the Computer Science and Engineering and the Electrical Engineering Department from the Pennsylvania State University. And he is a leading expert in the computer engineering. His research interests are in embedded system design, computer architecture, and power-aware systems. And Professor Narayanan has many honors, and he is a fellow of IEEE and ACM. And his work is currently supported by the DARPA SRC, CRISP, and the CBRIC centers. So now let's welcome Professor Narayanan to give the talk titled Advances in Distributed Video Analytics. Welcome to Professor Narayanan.
Bo, thank you for the invitation. And one of the things that I would like to mention is I appreciate all the students joining in. I know how difficult it is for you to just join in remotely. One of the things that I do tend to do because of that is the reason I'm looking up right here, if you're noticing, I just have a bigger screen there with all the attendee list. And I tend to have a tendency to call on someone at random for questions or clarifications during my talk. So a colloquium will be no different for me than a normal classroom lecture. So I'm hoping, Bo, they can unmute themselves and talk back if I ask them a question. Is that true?
No problem. Yeah.
Okay, thanks. And if there are questions in between, you can stop me and ask me questions. I'm sorry I'm not there in person in the Rutgers campus to interact personally with you, but we'll make the best out of what we are. And in fact, that's really the title of the talk too, right? So it's about distributed video analytics. Can I actually look at all your video streams and extract things that are useful? You are understanding things? Are you collectively learning things? That's kind of the eventual goal. We'll kind of look at what's happening. And I learned that you're not able to unmute yourself and ask me a question, but please drop in something in the chat box if you have questions, and Professor Bo Yuan should be able to try and relay them back to me. This work is essentially done mostly by my students and collaborators. Just to know that it's just not a single person here, and I'm thankful to the SRC Jump sponsors and the CRISP and CBRIC for sponsoring part of this work. So if you consider of what we mean by what's the need for these multi-camera systems and multi-view systems, you have a lot of different types of distributed systems emerging, and one of the more popular ones are these type of drones. And there are also other type of multi-camera systems that are really looking at things from a different viewpoint, and where the computation is done is another key issue in these distributed systems. Is it really done in the edge among the peers, or is it actually the inference and intelligence, is it kind of distributed between the edge and the cloud, or does it completely reside in the cloud? All these type of things bring important aspects. This talk will primarily focus on the visual modality of these sort of distributed intelligence. While I take visual as one of the parameters in this talk, many of these things kind of expand themselves to other type of sensing modalities. The part that you saw in the video on the left side is essentially work that we have been doing with Arijit Ray Chaudhary from Georgia Tech, where we actually have been trying to mimic some of these multi-view, multi-vision systems in a simulation environment called Pedra, which is actually open source if someone wants to go and look at it. And Pedra was developed by Arijit and his team. We have also been building other type of embedded systems where multi-camera systems are actually very common. This is a deployment of a live insect trap that me and my colleagues, this is actually sitting in Oregon, or rather was sitting in Oregon through the summer, looking at all pollinators and insects. And here you can see there are 3 cameras that are there, because these insects are very small. So you actually need to look at them in multiple views to be able to kind of recognize what is happening. So that kind of tells you the type of multi-camera systems that I'm interested in, right? So you get multiple views, either because a single drone moves around, or multiple drones seeing the same thing, or multiple cameras looking at a small thing like an insect in some of our insect traps. So those are kind of the motivational aspects. But the fundamental question remains the same for both these environments. If you have all these different views in which you are seeing this object, which views are most useful to recognize the object? How many views do we need? And these things become very important because we are really looking at embedded systems and battery powered systems or energy harvested systems. So power is a challenge. And these are also edge nodes. So if they are basically transmitting some of these views to do recognition elsewhere, then its communication is expensive, both in terms of connectivity as well as in terms of the energy expended in communication. So we want to try and get the most views. And of course, there are very many interesting things when people think about, hey, what if it's just not multiple views? I start getting 3D cloud points, and I'm starting depth information, but sparse depth information with 2D views. If you want to learn about that, you probably need to get back to me in about 6 months. Those are things that we are experimenting with as we speak right now. So if you look at what my talk is going to look at, I'm going to start with the notion that the edge nodes are not as powerful. So there's a need to try and work with a cloud to try and communicate these things. There are multiple sensors, and in this case, camera sensors that are actually acquiring the image of a single scene from multiple views. There could be individual camera failures. The communication bandwidth between them is expensive and could be prone to failure. So that's kind of the environment in where we still want to be able to try and get the best accuracies using collaborative views, but at the same time, try and reduce the costs associated with these inferences. And I typically go to the Design Automation Conference regularly, and in 2018, and this is actually a design challenge that happens regularly in at DAC. This system design context actually kind of brought out that it's probably very easy to try and get things done with data sets, right? However, when we start doing with real world, things get complex. There is brightness, there is scale, there is the view angle, there is occlusion, and all sensors do not have the same importance. And if we really start thinking about real world scenarios that we would be interested in, not all sensors would have the same fidelity. It may have been taken by different people with even mobile cameras or whatever. So the key thing is the motivation for multiple views and fusing them is pretty obvious to most of us. So the part that we want to try and land up doing, and to start doing these experiments, we work with Professor Lauren T.T., who's also part of the CBRIC Center, and his iLab ATM data set, which actually gives you views from 80 different angles and viewpoints that are generated. And we also use the iLab 20M from Ali Borji data set from the CVPR paper. So working with Lawrence data sets from these two sets, we actually use this to try and figure out some of our questions. Are there certain views that are better? How would we choose optimal number of views to try and balance these computation, communication costs with the need to get good accuracies? And these data sets are available for everyone if you want to try and reproduce or play around with this stuff. So one of the key notions for us to be able to answer the question, is a view important, right? As a human, it's very easy for you to recognize, oh, this is useful view, this is not useful view. But what are qualitative or quantitative metrics that a machine can use to try and deal with this? And one of the things that we landed up honing on was actually entropy. And of course, we use entropy in all these machine learning epochs. And essentially, if entropy is too high in these cases, it basically, if it's a low entropy, there is a high likelihood that it belongs to this actual data set. So we can think of the quality of information against a trained network is inversely proportional to entropy, and all these DNNs are trained. So if we basically land up getting a very low entropy, we basically know that the quality is pretty high. It matches something that was trained. So what we can land up doing, if we acquire an image with a high entropy, we can probably throw it out because it's not really matching with anything that we are looking for in our part. The other aspect that's very important in these type of distributed systems, especially when you start applying these deep neural networks, is how is the model going to be built, right? So the model that we start using in this case is basically a single model that's kind of distributed across all these multiple sensors, where you have local CNN stages, which are then pooled together from each one of these camera views, and then you have a secondary layer of CNN that basically processes these aspects. So one of the things, this is actually from, this is our baseline from work in ICCV from 2015. However, as you note in this particular case, all the cameras need to kind of communicate with themselves. So there is exhaustive internode communication. And there is really no notion of importance selection in this baseline that we choose, which is kind of the state of the art. It basically takes an average viewpoint from everyone to try and land up doing the final acquisition. And one of the things that should probably be very clear to you, when you start averaging from multiple cameras, there may be cameras that are not even showing your object of interest. So if you kind of diffuse the information by taking all irrelevant things, then things become murky, right? So you don't get much if you're getting viewpoints that are really not targeting what you want to see. So more views does not necessarily mean good. And that's really the problem with this average selection, which kind of weights everything similarly. And of course, the bigger challenge in this case is the number of views has communication cost, not just accuracy cost. So of course, if in many cases, if you are able to try and increase the accuracy, it's also landing up increasing the communication cost. And you can kind of see the improvements in accuracy is not kind of commensurate with the benefits. So we are looking for some feature aggregation to make sure some of these views could be combined together before being transmitted, or we are looking into scenarios where you can kind of drop some of these scenarios, or you can do proportional transmission of these type of things to try and get the benefits of more views, means more accuracy, while trying to eliminate this communication cost. So if you look at one of the aspects in this scenario, the metric to evaluate which information is needs to be transmitted locally is really critical, and we also want to make it blend with the existing feature extractors that exist. So if you really look at networks like the Google Net, it's actually hierarchical in the sense it has a feature extractor layer and a classification layer. And what we'll end up trying to do is actually use this feature extractor layer, which runs locally at the edge, to try and understand what are the features, what are the quality of this based on the entropy metric. How should we weigh this as we move on to the next layer? And we kind of use the pooling layer between these two stages, CNN A and CNN B, to be able to determine whether that feature proceeds further, with what weightage should it be pulled together to go to the next stage. And we also end up doing some context grouping of cameras in the early features as well. So those are two different techniques that we end up doing. And as you can see, this kind of fits the partitioning between the edge and the cloud pretty easily. So the CNN A runs on the edge, the CNN B part runs on the cloud, but the entire model is trained together. So that's really how things work. Now let's kind of get a notion of entropy and how it comes into play. So let's actually consider just 4 views of a single object. Of course, if you try and train something on view 1, that's kind of the top left quadrant that you see in this. If you then supply it with view 1 for things that were trained on view 1, you can essentially see that it has a much higher confidence in making those type of recognitions. And again, the same thing with view 2. But you also notice there are some scenarios where you're landing up trying to figure out scenarios where you're getting better accuracies with other views as well. Can we kind of understand these things from the entropy metric and utilize them? So that kind of leads us to this overall view that we land up having in this particular system, which tries and groups together cameras next to each other in what we call as context groups, because they are providing similar contextual viewpoints. And that's kind of called as the context group. So this is with supervision of training data. Then using the entropy, we calculate a metric for likelihood. And the likelihood gives the notion of node importance or the view importance. If the view is more important, you would like to weight it more in the view pooling phase when you combine it with different views. So for example, if there are 3 students in the class, Kaustav Jadhav, Kimberly Chang, and Kyle Hunt, if Kimberly is able to see things much better than Kaustav and Kyle, we would probably weigh Kimberly's view much more than Kaustav's and Kyle's view in this particular scenario, right? So that's kind of it. And let's say there is another viewpoint, which is Vijay's viewpoint, and his view is not really clear. We can even drop his viewpoint because you think it's not important, right? So, but let's not drop here, because then you will stop listening to me in this particular talk. But jokes aside, let's kind of look at what happens next. You take all these importances and do something similar to average pooling, but now a weighted average pooling. And now this is what lands up being used by your global prediction. Understand that the view pooling weights land up getting only things that were transmitted beyond an importance threshold. So there is a communication drop already done at that point, and things that land up coming here, you again weigh them proportionately so that it influences the secondary global prediction that lands up happening. And again, all these things happen at the front end, and these aspects happen at the back end. So there are two key concepts happening in that network. One is at the local node, we are calculating the likelihood based on this entropy calculation that we are landing up doing. We are setting up a threshold. If it's less than a certain threshold, we are basically signaling it's zero importance. So we are not necessarily even transmitting that feature. That's really where the communication benefit comes. And then at the back end, we also have a proportionate importance for each views, and these are essentially at the inference stage. These are all deciphered at the inference stage, so it's not necessarily static. So as we will see, this makes it robust for certain dynamic things that happen in these multi-view camera systems. So if you want to look at all the results and other stuff, you can look at the DAC 2018 paper on the JetCast 2019 work from Jinhang Chai, who's now at Microsoft Research, but was a PhD student at Penn State at that time. We are able to decrease the communication energy cost by about 3x with very little drop in accuracy. And we'll also kind of show how this is resilient to individual camera failures in the next few slides. Are there any questions at this time? Bo, you may need to relay the questions if you see any, please.
Yeah, I think there's one question. So whether this method increased the computation power required at the endpoint?
So that's actually a good point. So if you look at some of these networks, based on what you think of the endpoint, we already have drones that are actually doing, in fact, the entire Google net on the edge node. So we basically drop them with some of these USB plug-and-play GPUs, and we are doing this. We are also building FPGA accelerators that can connect to some of these drones and compute these things. So computation increase is there if you start doing the inference at the node. And so that is also the reason why in the second part, I will really look at how to make some of these computations feasible at an edge node. Okay, so we'll get to that. That was a good question. Thanks. Any other questions? But one thing that I want to emphasize, I'm not repeating computations. I'm actually making use of this hierarchical structure in GoogleNet to be able to do this as a two-part design, where the CNN-A and CNN-B would have typically been done only at the edge, but now we are doing the CNN-A part at the edge and the CNN-B at the end. Was that clear? Okay, any other questions? Bo, do you see anything?
Yes, and actually, myself also have a question. So here, the CNN used in the different nodes, they will be kind of the same or can be also different. For example, some nodes use the inception, and some use like the models like kind of more target for the object detection, like the fast RCNN, something like that.
Yeah, so the one aspect to put, Bo, if everyone else could mute yourself when you're not asking a question, that would be good. I kind of hear an echo, maybe others are hearing it too. It's gone right now, thank you. Bo, the challenge of using different networks in different edge points, at least right now, is because our model training, we train the model as a single model. So if you land up having distributed models, then training the model becomes pretty challenging from the different viewpoints. So it may need some perturbations to what we land up using currently. So the model training is a challenge as well as in the distributed learning environment. So our current model will just not land up to a plug and play of different CNNs elsewhere. If we can work around the training, then conceptually it should still work well. But I don't know how easy or how tough until we try that out. There was one more question that came, and I'll take one more question before I move on to the next set of slides.
Okay, thank you. There's another question. So does each sensor CNN only identify one specific view of an object? If yes, if we need to train them using the samples of a specific view of this project?
So one of the things that is true is our training set has about 80 views. But as you kind of mentioned, I may not know which view comes from where. So you need to probably calibrate which view belongs to what. Sorry about that. We have to calibrate which view corresponds to what. And that's something that we have done in practice. This system where we showcase in the actual paper, we are assuming those views correspond to the specific views. When we build an application, there is an additional step which actually associates the view with a trained view. To basically kind of get the identifier in this case. So in things like the insect trap embedded systems, our viewpoints are kind of fixed, so we can kind of land up associating a camera with a particular viewpoint. However, if you kind of think about these type of drones, based on the positional location of the drones, they may be looking at the view differently, or based on which direction the object is, things change. You would need an additional step to kind of orient the views onto the trained viewpoints. So that's again a good question, but practically we can do that mapping without too much difficulty. So keep the questions coming, and also send me more questions. Even if I'm not able to answer everything live, I'll try my best to answer you offline later today. Okay, so please keep them coming. That's really the only way that I feel excited. So if we cross 50 questions from all the 73 people, that would kind of make me happy today. Okay. So let's kind of look at what's happening with these different viewpoints. So there are these 12 view camera systems and 80 view camera systems that we tried to play around with. And now you can see when we club these contexts, and then if we use the normal max pooling versus average pooling versus weighted average pooling that we land up using, we can start seeing that there are scenarios where our weighted average pooling is starting to perform almost similar to the standard max pooling, and it's doing far better than average pooling, which is just saying all views are necessary, so I'm bringing all the views. So not only does it reduce the communication with the average pooling, but it lands up trying to get you the same accuracy. And note, for max pooling too, you need all the views, right? So you wouldn't know what is max until you get to see all of them. So that's really the power of the weighted average pooling. So of course there is a trade-off. There is a trade-off between the accuracy loss for not getting everything, and of course there is the benefit for communication cost. And the chart out here kind of gives you more of accuracy, because accuracy is both precision and recall, and you can see this in a lot more detail in this case. So let's kind of look at what happens when there are camera link failures and noise. So one of the challenges when you start doing this weighted importance, if the most important views start failing, then it becomes problematic. So for example, in this colloquium, when there are noises from my cell phone, as you probably heard, it's much more harmful than any one of your nodes having a noise that ends up coming up into the system. So if there is a noise at what we thought is the most important one, then our classification gets messed up even worse in this type of scenarios. So to kind of look at what's happening here, our weighted average approach is just taking 3 views and getting to the same level of accuracy as what average pooling is doing with 9 different views to get to the same level of accuracy, right? Of course, it's based on the notion that we identify which are the 3 most important nodes. And in our case, we did that using this likelihood metric that is there. So one way we are very robust, because if the noises are happening at a random way, then given that we are only working with a subset of nodes, when the errors happen at the non-representative node, our robustness is actually very good. However, if the failure becomes more uniform and across many nodes, then we start getting a huger hit in the actual accuracies that you'll end up seeing, right? So it is good if it is a sparse failure and the failures happen in the non-representative nodes. If the failures happen in the representative nodes, it's problematic. If the errors are happening for a larger fraction of noisy nodes, then it's likely that representative nodes are getting more impacted. In those type of scenarios, it is bad. So we have actually played around with 2 different models. One model is if you don't know whether it is which view, which sensor is getting impacted. So one way to end up dealing with this is we kind of tune the scale for our importance. So rather than saying, let's say someone who has a PhD has 100 points, someone who has masters has 50 points, someone who has an undergraduate degree has 25 points, right? So rather than have a dramatic variation, I would say someone who has a PhD, I would give them 55 points. Someone with a master's, I would give them 50. Someone with a bachelor's, 45 points, right? So I basically scale the magnitude of importance that I give, but that was just an example. I believe in my own notion, I believe everyone is equally smart. So whether you're a bachelor's or a PhD or master's, it doesn't matter. So my weightage was just an example, not implying someone should be more important than the other. So that was just an example to make it very clear. So when we do this rescaling of the importance, we notice that we become a little more robust to some of these errors. However, we again spike in the communication cost. So it's kind of a hard challenge. We can make it a little more robust, but you again pay in terms of communication cost because you need more. However, if you have known failure scenarios or known attack models, if you know, oh, this camera that is at this viewpoint is more prone to errors because as the wind blows, the tree is going to block that particular camera, so I know it's not going to work very well. Or you basically know, oh, that camera is coming through a connection that's weak. So then if you are able to selectively tune this importance, knowing a priori notions that of likelihood of failures, then we are able to recover in these accuracies again by tuning the weights based on the likelihood of failures that happen. So you can kind of play around with some of these design trade-offs. More recently, one of my graduate students, Zinab Hakimi, she's actually been playing around with adding some new aspects to this. So she wanted to try and explore, can we play around with more universal set of importance estimators? And another part that she wanted to land up hey, is it better to actually transmit the original image space rather than the feature space? Because feature space sometimes is much larger than the image space. And then she also wanted to kind of say, hey, should I even transmit the entire image, or can I actually do a subsampled image back, right? So those were all aspects that she wanted to try and land up doing. In addition, at the back end, she wanted to make use of some of these learned mechanisms to try and create a super resolution enhancer that would just take a low resolution image, enhance it, and then do the classification. And she wanted to try and figure out, does that actually help in the overall system rather than just doing extrapolated super resolution at the backend system. So just to give you some design space explorations that were happening in this particular case, she tried attention mechanism called as saliency that's typically used by the human brain, for example. So this is actually a center surround difference type metric. That's what saliency is. And what she ended up trying to do is she ran a metric which counted the number of pixels in an image that came out as salient. Based on whether it crossed a certain threshold or not, she decided to send the entire image in high resolution or a low resolution for the backend part. And as you can see, there is a trade-off between the communication cost that declines. However, in this particular importance metric, the accuracy seems to be almost tagging the communication cost reduction. So it didn't turn out to be that great a metric. This gave us, again, the notion to evaluate how good entropy was in this particular context. And you can kind of see entropy works a little bit more in our favor because it seems to be the impact on accuracy up until a certain threshold is much more flatter for the significant benefit that you'll end up getting in communication cost. And the notion of finding an importance selector continues to be an open challenge. And all of you can go back and look at making things better than what we have accomplished. And that's really what I'm looking forward to as well. There is also things that have been done based as follow-up. So Professor Anand Raghunathan, who's also part of CBRIC Center, he expanded upon our initial idea to do this significant based feature resolution and pick up features at different scales and different bit widths. And of course, we have done this in the multi-resolution space. The important aspect that we figured out when combining this learned super resolution with these multi-resolution images, we landed up getting substantial energy reduction in the front end for minimal loss in accuracy. And again, one of the things that we all run on when we start thinking about CNNs and other stuff, you're looking for the 0.1% improvement or 0.05% improvement. And now you're saying, hey, this guy is telling me 2%. But believe me, when it comes to deployment, a 5x reduction in energy makes the difference for me to be able to deploy my insect trap system in a solar powered environment unattended for a month, or should I go and replace the battery in about an hour? So that makes a huge difference in deployment scenarios. And some of these things I can probably tolerate a 2% loss in accuracy and still get the desired outcomes of things that have not been possible before. Any questions at this point before I transition to the last part, which is going to talk about more of architectural support for the edge analytics?
Yes, here's one question. Did you experiment with scenarios in which the camera placement was more approximate, that's different than link failures? Or is the camera placement just to look at different shapes of configurations?
Yeah, so the camera placement is not really a critical challenge. As I said, this is actually just the learned model is a unified model. So if the camera views don't necessarily line up, it's not going to impact. However, having said that, the iLab 80 and iLab 20 data sets are data sets that were actually created using this fixed viewpoints. That is the reason we have now been starting to experiment things in a real application scenario with the Pedra virtual environment, and hopefully I'll have more validated comments to talk to you about. We also deployed the same environment in a real drone for our object. We actually tried to develop a drone for picking up garbage. Actually, there was an undergraduate honors student who built that. We have been able to validate some of these multi-viewpoint stuff actually end up working even without a specific reference. So in short, I believe we haven't seen a substantial impact on it. But having said that, we have also not necessarily thoroughly evaluated it in all these contexts with just that question in mind.
Okay, thank you. Another question: okay. With high-speed mobile data starting to be, does this make sense to centralize all the extraction on server side itself?
Yeah, so one of the things that's actually an exciting question, and in fact, I will be starting on a project with the Jump along with multiple centers in January. It was just awarded as recently as yesterday of something that we have been working on for the last 3 years together with people at multiple universities. One common thought is 5G is coming, communication is cheap, the cost per communication is reduced, so you can actually, when I say cost, the energy per bit is reduced. So and there is a prevalent notion that now compute is the bottleneck, so why not just do everything in the cloud, right? So there are many reasons why I would not want to do in the cloud. So if I'm basically, and one application that I actually end up working in a different project in the NSF Expeditions in Computing, we actually work on cameras actually assisting visually impaired people. I do not want the feed that I do personally to be transmitted to a cloud. I would like my privacy to be very important. So there are many reasons why you would still need things to be done at the edge. And with many of these new accelerators that I'm able to show, the cost of compute is still much cheaper than the cost of transmit when you start thinking about concurrent progresses in both the dimensions. So also because of personal reasons, if there are ways in which I would not necessarily transmit everything that I needed to do a cloud and I can do it locally, I think most of us would still like that, right? So I am for one convinced that there is going to be this notion of more and more edge intelligence that is happening at the edge. And also for many of the applications, as I said, like when we monitor pollinators, we are actually deployed in things like Allegheny National Forest and some places where there is not necessarily a good connectivity to something remote. And of course, you can think you could have a multi-hop network that goes and connects to a satellite and transmits. But again, those basically fundamentally alter the capability of what you can and what you cannot do. So edge intelligence is almost a prerequisite for actually opening up these type of barriers. There was another question that popped up and popped out. So Bo, could you please read that back to me, please?
I don't think so. I think right now that is all the question we have.
Okay, thank you. So let's kind of look at what more. So I just talked about video analysis and object. It was more like object recognition that I actually talked to you about, right? But in practice, some of these things you're actually monitoring a security camera, or I'm actually monitoring a live camera to look at insects interacting with a flower, or I'm actually looking at an animal trying to move around that's endangered. So I'm trying to learn about these type of things. And of course, that can just be motivated from what we are seeing in things like YouTube and other videos that you're seeing. Or maybe, given that we are all remote, many of our classes are being recorded, right? And things are being stored. Would it not be very nice, rather than me having to listen to everything my instructor says, would it be very nice if I basically get a summary of what the instructor said very quickly? So 1.5 hours of lecture, if I can summarize this in 15 minutes, that would be wonderful, right, for all the students. And for that matter, it would be good for all instructors like me too, if you have that capability. So we are actually looking at a transformation of these from archival store and play videos to interactive video content analysis. And this is not only useful in the classroom scenario that you talked about, but it's good for doing this video content analysis. So can I really do this automatically by looking at all the frames and trying to do content rating, rather than these days when you upload your video to YouTube, it basically says, is this made for children, right? So you have to manually use it, but can you land up doing many of these things automatically? Can you do content-based queries? I'll show you some of those things. And of course, with the election around next week, we have been learning a lot about synthetic video generation and other stuff. And of course, there are many ways that you can use synthetic video generalization rather than to get back and forth between two adverse political campaigns. It has a lot more uses in these particular scenarios. For example, what if I can actually contextualize, let's say, help for voting in terms of who you are, right? So based on whether you are in New Jersey or Pennsylvania, maybe I'll show you some content manipulation down there on the fly based on what it is doing. So there is a lot more in visual analytics that needs to be done. We have been playing around with some of these different type of systems. So when a video frame comes in, you may need to be able to land up extracting features from them. That's really the ingest part of it. But it also needs to be able to do queries, summarization, matching to a text. What ends up happening in many of these systems is when you have the video, it basically runs some of these deep networks and then adds metadata with this frame, which says frame 1 has cat and dog. And then when you're actually trying to do a query, it's basically trying to use only the metadata, but it's not necessarily exploring the actual images themselves. Then there are some of these video analytics frameworks that land up doing the feature extraction, but then it's also able to apply some attention network across the different features, across the frames, and then provide, let's say, a summarization. So if you have a 1 hour long lecture that you're going to listen, it could probably encapsulate that into 5 minutes. And I would be very interested. I've not tried this on lectures yet, so it would be interesting to see these type of things there. And then there are things where you are running something a little more interesting, where you're looking at the video and then you're querying using text. And then it's not just comparing with the metadata, but it's actually going and running this extractor on the actual video frames themselves, right? So the whole question is, can I start doing many of these things on my edge node? And maybe some of you already noticed some of these type of features do exist in your cell phone, but they are still making use of the cloud rather than doing everything at the edge in this particular scenario. So if you kind of start profiling some of these compute intensive stuff, it's not just DNNs. There are things that need self-attention, regression, RNN, content similarity. And one of the things that we have been trying to do, how would we be able to accelerate many of these applications on your mobile devices, on your edge devices, right? So, and one key aspect to do these things is Also to try and understand there are multiple variants, multiple capabilities that end up happening. We have been working with Professor Songchen Su's group at UCLA on doing 2D, 3D scene reconstruction understanding and skeleton-based human action recognition. One thing that's common in many of these things is that the memory is a key challenge. The volume of data is very high. And so consequently, I'm going to skip this particular video, which kind of just shows, if you have this video, we are now able to land up returning this query. And this was essentially built on the software framework for QVSum, but we actually have a hardware emulation of this entire system to kind of make it in a factor that's useful in the embedded domain. So that's kind of that system. But what I will focus on in this particular aspect is to kind of point out, when you have a video analytics pipeline during the ingestion, on the fly processing of these video frames, you still have to deal with a lot of these compression, decompression, encoding, decoding. These are traditional things that we are used to. We have all these emerging deep neural networks, and then based on what you want to do, you extract features, specific features, or whatever. And then you would need to support queries that can happen either through a deep network, RNN-BERT model, or it could actually happen using anthology graphs and trying to match different aspects. You want to summarize these things. So you have a lot of different kernels that you can identify. And one key objective that we have been looking at is in developing processor in memory structures for these things. And I'll kind of, the primary motivation comes from the fact that data movement is expensive. And as the model sizes and the data associated with these models increase, that becomes a major part. So if you really look at even data being moved within on-chip L3 cache, 90% of the energy or more is actually both for latency and energy expended in just the data movement. Even when you start thinking about all these cool accelerators that happen within in-cache processor, a lot of energy is expended in moving and shuttling data from the main memory. So data movement is really expensive. And I'm going to give you a snapshot of very few a few ideas that are capable of being employed across the stack for these type of accelerators. So there are many different ways in which people are doing PIM, but I'm going to be focusing on lookup table-based compute engines, because lookup table-based compute engines can be deployed SRAM, VRAM, orthogonal to the actual implementation technology. And it is something that we also have implemented in L3 cache environment, which is what I'm going to zoom in and kind of explain what it ends up doing. So what it ends up doing is it realizes that in a memory, you have lots of parallelism at the subarray and array level. So you can essentially try and do computation for all those data at the same time in parallel. And the way that it is doing the computation is, if you want to do, let's say, A plus B, what you'll end up doing is store a lookup table, which basically has entries for every combination of A plus B. And of course, that would be start becoming prohibitive if A and B become pretty large and the size becomes large. However, if you start doing bit slicing of that, and if you start using properties that A plus B is commutative, so A plus B is equal to B plus A, then these type of things become pretty reasonable and viable to do. So in a way, looking up to the lookup tables where the data exists is actually the processor. And there is a small compute engine, which is a state machine that's kind of helping you index into the specific lookup tables based on the data that's fetched. So the way you think of this is a small compute unit that's interspersed locally within the memory, that's kind of interjecting the data that's coming in from these subportions, and then using the lookup tables as the compute engine and constraining the entire manipulation within that particular subarray without it having to traverse in and out, which we saw was 90% of the cost, right? So if you start doing these type of computations and leverage some of these optimizations that I say for multiplication, addition, and whatever, and there is a real rich literature on these type of optimizations in lookup tables developed for FPGA-based designs and these Cortex designs. So a wide variety of applications like activation functions, everything fit in these type of lookup table approach. In addition, as I said, data cost is important. So one of the other things that we ended up doing is we also start supporting these communication structures within the subarrays. These type of structures already have been envisioned for some of these larger caches embedded with NOCs, but we embed these routers even at a finer level. When you think about router, I'm not really thinking about virtual channels and other stuff. These are simple fixed connectivity across the neighbors to kind of support some of the data flow, nearest neighbor systolic data flow that you can use to try and make these things efficient. So what we'll end up doing in these type of accelerators, if you have a CPU that has a large cache, we switch that cache to an accelerator to do these type of DNNs. We'll do loading of all the weights into the cache, and then we load the configuration into the slice controllers, and then do the computation. When you end up doing these type of things and evaluate it on a variety of these models that I actually require, you'll end up getting significant performance gains and energy gains compared to even other in-memory solutions or other accelerators. There is a lot more effort that's actually required to land up trying to get these type of advances going to be able to support more and more advanced execution at the edge. And once we are able to do a lot more on the edge, then a lot of these things of distributed, which to select, what to select, becomes even more interesting in this space. I'm kind of going to quickly just flash things later on. If you're interested, just to trigger a conversation later on. We have done these type of models for LSTMs and transformers. We have also built similar things for recurrent neural networks. Again, one of the key things in designing a lot of these accelerators, it's just not about hardware design or technology. It's about fusing advances in math, the network intelligence, implementation technologies. What technology will you implement these things efficiently? Paying very close attention to an overall system viewpoint of where data moves, how data moves, and all these things. And also not losing the fact, finally, you need to be able to support applications and real systems that may need video codecs, it may use graph data structures. And then when you start applying many of these optimizations, in an ideal world, you may have load imbalance, synchronization overheads that may all need fine tuning. And one other thing is a lot of these things are sparse. You may need to be able to, when you start thinking about many of these accelerators, they actually do not really exploit the sparsity in the execution, right? So they transform the sparse compressed representations to representations that open up each element. The ability to compute directly in the sparse domains, as I can show out here, if you just need to compute one multiplication or addition, if you basically do it in the uncompressed format, you're doing a lot more unnecessary zero-based computes. Even if you eliminate them using some optimizations today, it's not ideal. So there is some work that we are currently doing with colleagues at Intel to be able to support this dynamic, dense, sparse transformations and computations to avoid these type of things. And there is a lot more going on in my lab on interactions between technology, computations, and efficiencies. And that's really what time that I had to share with you today. Thank you. I will wait around for a couple of more minutes to take questions if you have the time, and if there are people who need to drop out, given that it's 11, I am completely understanding of that fact as well. Thanks.
Thank you very much for your very. Hello? Thank you very much for your very excellent talk. And I think I missed one question. Let me try to find that. So there's one question about the video analysis. So does the view importance estimator located in the back end, even if the system knows that some sensors are not important, are all sensors still transmitting data? Can the system select important sensors to transmit data?
So this is the important aspect in this case, right? So we really do not know. This actually goes back to the previous question, right? So if you're recognizing my face, you know this view is best, right? You're seeing my face. If I turn around myself this way, you're not really understanding who I am. So it's not, but whether whether this view is the best also depends. Now I'm not moving my face, but I'm moving my camera, right? So in a dynamic environment, I do not know a priori whether a view is important or not. And that's really the biggest challenge, right? So it is not like I label that this camera is important or not. What we are trying to do is we are using this entropy metric or the saliency metric to be able to dynamically identify whether a view is more important or not. The task of actually labeling a static importance estimator just based on, oh, this camera is placed in a place where I think someone is going to break my camera, or I know it has a poor lens. That part is a lot more easier than the dynamic detection that we need to do. And of course, many of the things that you land up saying, if the backend knows which camera is a lot more reliable, can it actually ask to send that data alone? Rather, it actually does even better. It's basically asking everyone to send its viewpoint, and it can actually weight things together accordingly. And maybe this is really the key thing that you are asking. Right now, our importance metric is one way. The local node kind of estimates its importance, and that's based on a metric on the quality of the image that we are seeing. Maybe there is a nice way to influence what you're saying. Based on analysis of all the sensors, it can probably go back and feedback, especially in a video context, given that there is temporal information. You can probably go back and say, suppress this camera. Maybe it is cheating that it's more important, right? It's really not processing the video, but it's sending me junk and saying it's important. And that probably is a good issue when we start thinking about hacking a camera view and other stuff, where you may need the backend to also go back and say, modulate your importance. You are no longer important. You're cheating me or whatever, right? So that's kind of an interesting aspect. We have not looked at that yet. And those are aspects that will come up when you start thinking about temporal locality of these importance in video streams. Thank you.
Thank you very much. Here's another question about the PIM. And we know that the random PIM is a very popular, a very hot topic in the architecture. And so this asks questions. So what is the current challenge of PIM? And the PIM used is used for SRAM or can also be used for the DRAM?
Yeah, so the biggest challenge with PIM, to be very clear, it's not necessarily the technology challenge that comes in, right? So it's the usability challenge, the programmability challenge. So one of the common things that you hear from PIM in a very traditional sense. You cannot add logic in a memory process. The logic will be too slow or it will impact the density of the memory. That is not the prime driver today. How would I be able to make use of these programming in memory features? What should be the computation supported in these things? The examples that I showed you were SRAM. However, as I told you, the lookup table is amenable to things in the DRAM. However, there are significant challenges in the DRAM because one of the primary challenges for DRAM PIM is because of the interface design. Because you stripe the data across different DRAM chips. So even if I want to work on one large word of data, those data are striped across different DRAM chips. So I need to be able to, I really have to gather data from all the chips to do the compute. If I change the striping mechanisms, it's going to play around with a lot of this error checking codes and a lot of striping stuff. So one key challenge in the DRAM, PIM stuff right now is legacy interfaces. How do you overcome those type of challenges, right? So that is the primary thing. But from a technology viewpoint and a realization viewpoint, the technique like a lookup table is pretty relevant to the DRAMs as well. And there's also work being done in the context of other emerging technologies, and many of the things that I showed you were based on cross-point architectures based on resistive RAMs, for example. And there is also some work on things on solid-state devices. So the greatest challenge to me in PIM is trying to figure out what degree of computing is needed at what level of memory hierarchy and how to make it work with all the legacy stuff. Because as you add PIM to a DRAM, your existing applications need to work as well as they used to. And some of these new things and old things don't necessarily have the same requirement. That's the challenge.
Okay, thank you. Thank you very much. And then another question is asked whether you would like to share the slides.
I'm fine with that, thanks. I do not know whether you recorded this or not, but if you did, you're welcome to use my lectures.
Okay, thank you.
All of you have a great day. Thanks for listening to me. If you have any questions, please do feel free to drop me a note. I would not promise you to respond right away, but I'll do my best to respond to you. Thanks.
Okay, thank you. Thank you so much.
Thank you.
Okay, so this talk is being recorded and we'll post that on the ECE YouTube channel.
Thank you. Take care.